We'll do it after. Yeah.
Are you teaching any graduate classes next semester?
I have no idea. I don't know what I'm teaching yet. Yeah, I'm not sure. I know that there's I know about half the students in this class took 540 last semester. But that class ended up pretty well. And so I know some people were requesting that. So I did put a request in to teach that again in the fall. But we'll see. I mean, because we have other grad classes that we need to offer. And so I think that the complicating thing is that we only have so many grad students and each class needs to have a certain minimum enrollment. And we need to keep rotating all the classes. And so we have so many classes we haven't offered this one in 3 years or something like that. So we need to offer that one.
Okay.
And so even if a class was popular, even if it was in demand, we might have to offer something else in the meantime, just so that we have a good rotation of those classes.
Right. Yeah, I really want to take the advanced design and management class.
Okay.
But I don't even know when the last time that was offered.
Yeah, we have a lot of. I mean, that's the unfortunate thing is that people design classes, and then they leave, and then someone else can't really take it over, and so especially with grad classes, it's even more tough to do that.
There's a renewable energy one too that was on the list of classes like a year last semester. That one has disappeared, unfortunately.
What was the average? Like 35, right? Yeah, 35. Hey, Aaron. Busy. It's been a busy week. A lot of grading, a lot of dumb meetings, a lot of other stuff going on, but it's that time of the semester. Yeah. How are you? Yeah, everyone's really busy now. Yes. End of class today. Yeah.
Did you end up removing a question from the midterm 2 or something?
I removed half a question, and so what I was seeing is that the exam. I mean, I could see it when you guys were taking it. It was a little bit too long, and so I curved it by about 5 points. And so instead of being out of 50, it's out of 45. All right, it's 7 o'clock, so let's go ahead and get started. What the hell did I do? Done. Well, that was anticlimactic. There we go. Okay, it's 7 o'clock, so let's go ahead and get started. Go away. All right, so how's everyone doing today? Good, good. All right, and so I think today might be our last lecture, and so after today, I think we'll be done with all the content in this class, and then we'll just be working on the project from here. And I don't think we'll use the full lecture time today as well. Okay. All right, and so first thing I want to share with you, probably a lot of you noticed yesterday was the midterm scores were uploaded, and so the average was 35.8. Okay. And so, not that I have to say this, but I think everyone knew that I think the exam was a little bit too long, right? And so I decided to curve the exam by 5 points. So usually I don't do this, and so usually I just kind of let the exam scores fall where they may, and then I curve at the end of the class. But I think this is kind of an exceptional case, because as I was going through your exams, I was saying that it wasn't that you guys didn't know the material, it's just that you just didn't have enough time. And that was my mistake, and I never want my exams to be kind of like a big rush or big, race against time like that. But, this time it ended up being like that. And so I wanted to curve the exam scores to, to make up for that. Okay. So the average now is 35.8 out of 45. And so when you get your exams back, it'll say out of 50 on there, but on Canvas, I adjusted the maximum score to be 45. Okay. And so if you did score over 45, there were a few of you that scored over 45. That means you did get extra credit on the exam. So if you got like 47, 48, 50 out of 45, that means you scored just that much more extra credit on your exam. Okay, and so the plan for today is on Monday we kind of spent a lot of time going over what I call the algorithm, the isoparametric algorithm. And so today we're actually going to see it in practice, right? And so I have an example plan where we're going to go through every step in the algorithm and see how we can apply that with hand calculations. Okay, because even though the algorithm right now it's kind of nicely implemented in terms of how you can implement it in MATLAB. I think actually seeing the calculations kind of happen live in front of your face, I think is always a helpful thing to understanding, because it's one thing to kind of read an algorithm and then to implement it in MATLAB. But then if you kind of understand what everything that's going on while you're doing all these computations, it just makes it that much easier to fill that, to make those adjustments. Okay. So the exams will pass out after the end of class. And so are there any questions I can answer before we can get started today? Okay, all right, so let's go ahead and get started. So let me go ahead and scroll back to where we left off. Okay. All right, and so we left off doing this with this example right here, right? And so we have a trapezoidal element, and so we have our 4-node quadrilateral here. It's not a perfect square because it's not supposed to be, right? So the idea is that if we have this arbitrary element right here, and so this right here, this is a good example of an element that might show up, in a mesh, right? And so when you generate a mesh on a finite element part, you're not paying too much attention to the elements, right? So they're just gonna have whatever form that they have. Of course, you want to watch out for things like skewness. You don't want your mesh to be too skew, but you're going to end up with a lot of elements that look like this. Okay, so this is pretty typical right here. Okay. All right, and so what we have here are the physical coordinates of all the nodes, right? And so I have nodes 1, 2, 3, and 4. Okay, and those physical coordinates are given up here. Right? And so, just because it'll be useful later, let me go ahead and put everything here into a matrix. Okay. So let me put in a matrix like I think I want a skinny matrix, right? Yep. And so I'm going to list out all of the entries of all of the physical coordinates of the nodes into this matrix, and we'll use this later to produce a lot of the quantities in the algorithm. All right, so first we have node 1, and so node 1 here from the table above you can see node 1 has coordinates of 0, 0. Okay, so x1 is going to be 0, y1 is going to be 0. Okay. Next we have x2, y2. So x2 here is 1, y2 is 0.2. Then we have x3, y3. x3 here is 0.8. y3 is 1. Okay. Then we have x4, y4. So x4 is 0.2 and y4 is 0. And so this right here are the physical coordinates of the elements nodes. Okay. So that'll be useful later, but I want to make sure I pointed that out before we go any further with the algorithm. Okay. All right. And so of course, that's not all the information we're given. We're also given the thermal conductivity. And so we have a K value of 10 right here. Okay. We have a thermal generation function. The thermal generation function is 20x plus 10y. Okay. And for this element, we also have a Neumann boundary condition. So we're going to see all phases of the algorithm. Okay. And so our Neumann boundary condition is this 5 watts per meter squared. Okay. All right. And so this problem, what we're going to do is we're going to use the isoparametric element approach. To compute the element stiffness matrix and element forcing vector for this element. Okay. And so we're going to follow the algorithm that we defined in class last. Okay. So we're going to have to go through each step. Right. And so, of course, the algorithm involves doing Gauss quadrature. And so, for an element like this, that means applying it 4 times if we do a 4-point Gauss quadrature. Okay. Okay. And so we're going to use a 4-point Gauss quadrature. But, because this algorithm is pretty lengthy and at a certain point it just becomes repetitive, I'm only going to run through the calculations just using 1 Gauss point. Okay. Okay. All right. So that's the setup for the problem. So that's the situation. Okay. Any questions on this so far? Okay. All right. So let's go ahead and start running through the algorithm. Right? Okay. So let's go ahead and scroll back up here. Okay. Okay. And so we're going to go through each step of this algorithm. Right? And so the first step in the algorithm is to establish the parametric coordinates for the Gauss points. Okay. And so we have options here, right? So we were using a 4-point Gauss rule. And so our 4 Gauss points are the following. Okay, so we have point 1, we know is -1 over root 3, comma -1 over root 3. Okay. Point 2, we have +1 over root 3, -1 over root 3. Point 3, we have positive. Point 4 is negative positive. Okay, so we have -1 over root 3, 1 over root 3. Okay. All right, so we have to choose one, and usually it's best just to go sequentially. And so we'll go with this one first. Okay, and so in step 1 of the algorithm, okay, step 1, parametric coordinates of the Gauss points. Okay, we're gonna have epsilon g. This is going to be -1 over root 3. Okay. And eta g, this is going to be -1 over root 3. But of course, if you were actually doing this, you would repeat this algorithm 4 different times, and each time you repeat it, you would move on to the next Gauss point, right? So the next time you would do it, you'd move on to point 2. Next time you would run it, you move on to point 3, point 4, and so on. Okay. But since we're just doing this for the first iteration, I'm just going to choose, the first Gauss point there, right? -1 over root 3, -1 over root 3. Okay. Step 2. Now that we have the values of eta and epsilon figured out, we can use this to compute the values of the shape functions. Okay. And so there's 4 of them here, right? So we have n1, n2, n3, n4. Okay. All right. So first we have n1, and we're going to apply this at epsilon g, eta g. Okay. And so this is 1/4. Okay. Then we have 1 minus epsilon g. And so epsilon g here is -1 over √3. Okay. And 1 minus eta g. So we have 1 minus 1 over √3. Okay. Right. And so we have all numerical values here. And so we can just pump that into a calculator. And so we punch that in and we get 0.622. And so that's N1. Right? Then we're going to do the same for N2, N3, and N4. Right? And so I'm just going to go ahead and write those down. Okay, so N2. N2 is 1 plus epsilon g times 1 minus eta g. Okay. You punch that, or you perform those calculations and you get a 1/6. Okay. Okay. Then we have N3. You plug that in and you get 0.0447. And finally, we have N4. And N4, you end up with the same value as N2. So you get 1/6. Okay. Right. So notice we get numerical values here, right? Because, even though our shape functions, normally our shape functions are functions of eta and epsilon, right? But since we're performing Gauss quadrature, we're evaluating those shape functions at specific values of epsilon and eta, okay? And so we should get numbers, okay? So we're actually gonna get a lot of numbers throughout this process because, normally we have functions of these things, but we're plugging in for them. And so we should get numbers for, for all steps here. Okay. Any questions on this step here? Okay. All right, step 3. Step 3 is another kind of computation heavy one, but we're going to compute the shape function derivatives at this Gauss point. And so unfortunately, there's a lot here, right? And so if you're doing this in code, it's not that bad, but on on writing, it's going to be a lot of writing. Okay? It's because we have 4 shape functions, and each shape function is going to have 2 derivatives. Okay. All right. So there's no easy way to do this, and so let's go ahead and start grinding them out. All right. So first we have partial n1 partial epsilon, and so this is a -1/4. Multiplied by 1 minus eta g. Okay. Where eta g here is still -1 over √3. Okay. So we plug in for that, we get a minus 0.394. Okay. Then we have partial n2 partial epsilon, and so that's a 1/4 times 1 minus eta g. this is 0.394. Then we have partial N3 partial epsilon. We plug in for that. 0.106. And finally, we have partial N4 partial epsilon. And so that's a -1/4, 1 plus eta g. And so that's going to be a minus 0.106. Okay. And then we have all the derivatives on the eta side. Okay, so we have a -1/4, 1 minus epsilon g. Okay. All right, so I wrote them down pretty quickly just because it's a lot of repetitive stuff, but those are our shape function derivatives. Okay. Okay. All right, double check all the function expressions here because I'm noticing in my notes. That's why I was kind of pausing a little bit. There are a couple typos in the notes, and so I think these all the signs and everything here should be correct. And so make sure you kind of double check that. Okay, and so before we move on, just because we know it'll be useful in this form, let's go ahead and put this into a matrix. Because eventually what we're going to be doing is we're going to be multiplying this by, different matrices in order to compute things like Jacobians and things like that. Okay. And so the matrix form that we're going to put it in is a 2×4. And so the first row in this matrix are going to be all the epsilon derivatives, and the second row is going to be all of the eta derivatives. Okay. So partial n1, partial epsilon, partial n2, partial epsilon, partial n3. Partial epsilon, partial n4, partial epsilon. Okay. And let's just go ahead and fill in the values here. Okay, and so starting on the first row, we have a minus 0.394. We have a positive 0.394, 0.106, minus 0.106. Okay. Minus 0.394, minus 0.106, 0.106, 0.394. And so in that form, it'll be more useful to us later because we're going to use it to compute the Jacobian in 2 steps. Okay. All right, but that step right there was the shape function derivatives. Okay. Right. And actually, I know some of you are kind of moving past this part already in the project. This step is actually a lot easier because the shape functions for a triangle are actually a lot simpler than for a quadrilateral. And so what you should see is that the shape function derivatives for a triangle, they should all be constant values. And so you don't have to worry about plugging in a to g or epsilon g at all in there. Okay. One of the nice things about working with triangles. And so after this example today, we're going to talk briefly about triangles and what shape functions there are. You might have seen it already in the project specs, but I want to talk about it together as a class. Okay. So this step will actually be a lot easier than this. Okay. And so that's step 3. And so step 3 is the shape function derivatives. And so that's out of the book. Okay. Next, we do step 4. Step 4 is we need to compute the physical coordinates of the Gauss point. Okay. And so this is necessary, when we go to compute things like the element forcing vector, okay, specifically from the thermal generation term. Right, and so if we go up to our element here, of course I wrote over it with stuff, okay. And so when we're performing our Gauss quadrature, right, we're evaluating things at the Gauss point. And so the Gauss point is physically located maybe somewhere around here, right? So X marks the spot. Okay. And so we need to find out, what are the X and Y coordinates of this point, so that we can plug it into our S function here. Okay. And so here, this would be xg, yg. Okay. Okay, and so we're going to do that from this in this part right here. Okay. If you think back to when we did our coordinate transformations in Gauss quadrature, this is exactly the thing that you're doing when you're forming the function x of epsilon, or in 1D, or x of epsilon and eta in 2D. Okay. Right. The only difference now is that we're actually evaluating these at a specific location of epsilon and eta. Okay. And so if you're doing Gauss quadrature by hand, you usually do this at the end, and so you don't plug in the epsilon value until the very end. Here we're just kind of doing it up front, just because we have all the information that we need right now. Okay. Okay. And so let's do x first, and so we have xg. Okay. And so xg here will be all the x coordinates of the corner nodes, right? So this is going to be x1 and 1, okay, plus x2 and 2, plus x3 and 3, plus x4 and 4, okay? Where all the x values are given to you in the problem, right? And so those were given to you then. And of course, all of these n values, right? These are the shape function values, and these are computed in step 2. Okay. Right, and so the same thing for yg. So yg would be y1 and 1 plus y2 and 2 plus y3 and 3 plus y4 and 4. Okay. Where again, all the n values, those are going to be the same ones you computed in step 2. Okay. And so we do that for this particular problem because we already computed step 2. And all the x and y coordinates we knew from the beginning of the problem. We get xg is equal to 0.2358, and yg is 0.2280. Okay. Right. No units on these because the problem didn't give units, and so these are mystery length units. All right. And so here, now that we've kind of, done most of our computations here, I'd say this is kind of most of the hard work. And so now that we've kind of established, all of our shape functions, their derivatives, all of our physical coordinates, we still have some computations to go. But now that we've kind of did some work in putting this data in certain formats, this next step will be, easier than this. All right, any questions on this? Okay. All right. So next we move on to step 5. Step 5, we compute the Jacobian. Okay. And along with the Jacobian, we have to compute its inverse. My mouth said inverse, but my pen said determinant. Right, we have to compute its determinant, its inverse, and the Jacobian itself. Okay. Okay, so the easiest way to compute the Jacobian, now that we have the information already in this form, okay, is to take our shape function derivatives, which we computed in step 3. And so this is partial n1, partial epsilon. Okay. Right, and so we computed all of these in step 3, and in fact, we already put them in matrix form. Okay. All right, so all we have to do is just kind of summon that matrix again. And then we're going to multiply this by the physical coordinates of all the corner nodes. Okay, so this is x1, y1, x2, y2, x3, y3, x4, y4. Okay. Right, and this is something we've computed already too. So this is, I guess, this was prior to the algorithm. Let's say that we compute this in step 0. Okay. And so these matrices have already been formed for us, and so we just have to perform their matrix-matrix multiplication. Okay. Of course, if you're doing this by hand, it's a gigantic pain in the ass to do a matrix-matrix multiplication like this. But in MATLAB, it's a very simple thing. So you have matrix A, matrix B, meet each other, multiply, and then be happy, have a happy life, right? And so if we do this in MATLAB, what we get is our Jacobian is 0.4576, 0.0894, 0.0576, and 0.4394. Okay. All right, so that's the result of those two matrix-matrix multiplication, and you can verify that too. And so if you want to just do like the first row, first column, verify that you get that first number there. Okay. And so this is J. Right, so now that we have J, we can take its determinant. And so, we can use a function in MATLAB for this as well. And so this is 0.1959. Okay. We can also take its inverse. And so we can take, the MATLAB function for this inverse of Jacobian. Okay. Okay. And so this is equal to 2.2428 negative 4.4563, negative 0.2940, and 2.3356. Okay. Right. And so, this step is, not so much manual calculation. So, we already set up the problem well already. And so we just have to perform these multiplications in that. All right. Any questions on this? Okay. All right. So next we have the shape function derivatives in physical space. And so this is simple as well, right? And so, what we seek to obtain are the shape function derivatives, but in terms of x and y, not epsilon and eta, right? And so we want partial n1, partial x, partial n2, partial x, partial n3, partial x, partial n4, partial x. Same thing with y. Okay. But this is easy for us as well, because what we have is we have a Jacobian inverse, and we also have our shape function derivatives in the parametric space, okay? And so what we can say is that this is equal to, we have our Jacobian inverse, which we just computed. Okay. And we also have our shape function derivatives in the parent space. And so this is partial n1, partial epsilon, partial n2, partial epsilon. Okay. And so of course, this is what we computed in step 3. Right. And so, this is again, same case as step 5. And so we have these matrices defined already. And so we just have to multiply them in order to, in order to get what we want. Okay. Okay. Step 7. Okay. Step 7. Step 7 is to compute the thermal generation function. Okay? And so what we want to compute is S of xg, yg. Okay. And so this is a very simple step as well. And so we have 20 xg plus 10 yg. Okay. And xg and yg we've computed before. And so this was step 2. Or step 4, I think, right? Yeah, step 4, excuse me. Right, and so we go ahead and plug in their values, and what we get is 6.996. Okay. And once we hit here, we're basically done. And so now that we've computed everything here, our next step is just to save these quantities out. Okay. But let me go ahead and implement this in a slightly different way. Okay. Because it's one way that you can do this is you can simply just save it as a variable and then use it later. But I think the more intelligent thing to do was just to take everything that you've computed just now and add their contributions to the element stiffness matrix and element forcing vector straight away. Okay. Okay. Because that's ultimately what you're going to do with them, right? And so you're going to take these results And once you've summed up their contributions from all 4 Gauss points, you're going to add them together anyway. And so might as well just skip that step, right? And so save us some storage. And so we'll go ahead and add their values, okay? And so in code, it would look something like this. And so in code, it would look like KE is equal to KE, right? And so what we're saying is that the element stiffness matrix for this element, okay, we're going to add to it. And so we're going to say that KE is equal to KE plus, okay, we have our BG transpose multiplied by K times BG times the determinant of JG multiplied by the Gauss weight, okay? All right, so let me go ahead and label these steps. And so BG transpose and BG, these are both computed in step 6. Okay. And of course, the determinant of the Jacobian, this was computed in step 5. Okay. Right, and so now that you've computed these things already, you can just add them there. Okay. Similarly, we can do the same thing for FE. Okay. In terms of just the contributions from the thermal generation function. Okay, so FE here is going to be equal to FE plus NG transpose times SG times the determinant of Jacobian and G multiplied by the Gauss weight. Okay. Let me go ahead and label these. So NG we computed, that was step 2, I believe, right? Okay, so NG here, this is step 2. Okay. SG right here, this is the one we just did, so this is step 7. Okay. And determinant of G, this is step 5. Okay. All right. And so from there, we end the loop. All right. And so that's the algorithm in action. And so then you can kind of see each of these steps, taken by hand. Right. I wasn't planning on doing this initially, but just because I think it'll be helpful. Let me go through kind of a very shotgun, MATLAB implementation of this. Okay. And so we're going to go ahead and implement this in MATLAB in real time, just so you can see how it works. Just so that you kind of see my logic. So I think that'll kind of help you guys get started on the project. We're not quite done with this algorithm yet. We still have to do the Neumann boundary condition, but let me, since this is fresh in our mind right now, let me go ahead and implement this in MATLAB, just so you can see. Okay. And this should help you out with parts 1 and parts 2 of the project. Okay, so any questions on this before I jump to MATLAB here? Okay, all right, so let's go ahead and see how this is implemented in MATLAB. Okay. So this is off script, by the way, and so we'll see how this goes, because I don't have the solution in front of me right now. Okay. And if you want, I can upload this to the to Canvas afterwards. Okay. Okay. So let me go ahead and do this, just because I like to do this. Okay. Okay. All right, so we're going to go ahead and implement our isoparametric approach in MATLAB. And this is specifically for a 4-node quadrilateral. Okay. Okay. And so what this will do is that this will compute element stiffness matrix, element forcing vector, okay, for a quadrilateral element. Okay, so let's establish some variables first. Okay? And so first variable that we have is the thermal conductivity. And so for this problem, our thermal conductivity is 10. Okay. Next, we have all the coordinates. And so we have x1 is equal to 0. X2 is equal to 0, or excuse me, y1, 0. X2 is equal to 1. Y2 is equal to 0.2. Y3, X3 is equal to 0.8. Y3 is equal to 1. X4 is equal to 0.2. Y4 equal to 0.9. Okay, so first thing I'm going to do is I'm going to put these into a matrix. Okay, so let me say this will be a matrix. I'll call this coordinate matrix. So this will be x1, y1, x2, comma y2, x3, comma y3, x4, comma y4. Okay. Okay. All right. And for your project, of course, you would have to obtain these coordinates another way. Okay. And so, the way you're going to do this in the project is you're going to use the predefined nodes matrix. Okay. If you're not sure how to use that matrix, then we can talk afterwards as well. Yeah. So I'm not sure where you asked when you asked the question, Catherine, but yeah, I'll post this after the class so you can just watch right now. Okay, so next thing we're going to do, also in true fashion to the project, is I'm going to list out the Gauss points. And so in this case, we have 4 Gauss points. Right, and so this is in the same form as the project, and so I'm basically establishing the Gauss point matrix up front. Okay. Okay, so this will be the first Gauss point here. Okay, and so this Gauss point matrix, you can see it's a 4x2 matrix, right? So it's 4 rows and 2 columns. And so each row in the matrix will be a separate Gauss point, right? And so the first Gauss point is -1/√3, 1/√3, -1/√3. Okay. Let me go ahead and save my time here. So let me go ahead and copy and paste this 4 times. This 2, because it's annoying. Okay. Change to 2, 2. And the second Gauss point is a positive here. Okay. So we have 3, 3. And both of these are positive. I'm going a bit fast here just to make sure that I can get through the whole algorithm, okay? Because I do want to talk about triangles with today too. Okay, so those are our 4 Gauss points. Okay. All right, so now that we have this established, so we have the physical coordinates established, and we have our Gauss points established. Let's go ahead and enter our loop. And so even though in the hand calculations we did just 1 Gauss point, in true fashion, you would actually loop over all of it. Okay? So we're going to say for IG. Okay, so I believe that's the index I use in the project. In this case, we have 4 Gauss points. Okay? And so it's going to loop from 1 to 4. Okay? All right, so now we enter into the different steps of the algorithm. Okay, so first here we have step 1. And so step 1, establish parametric coordinates of this Gauss point. Okay, and so we want to set this up so that it reads the parametric coordinates directly from the GP matrix that we just defined. Okay, so it's going to be GP matrix IG, comma 1. It's going to be GP matrix IG, comma 2. Okay. And so if you're kind of following along with the in-class example, you would just kind of write this in minus 1 divided by square root of 3 And this would be -1 divided by square root of 3. Okay. And so if you're doing it just kind of by hand, you would do that. But we want to make sure that this code is smart enough to change the Gauss points on each iteration of the loop. Okay. And so to do that, we have to utilize our GP matrix. Okay. And the way we're using the GP matrix is that you can see the first index here I'm putting is IG, right? And so on the next iteration of the loop, then this matrix here is automatically going to update to the next one because IG is not going to be 1, IG is going to be 2. Okay. Okay. So that's step 1. And so after this step, you know, X, G, and A to G, that's going to have our correct values. Okay. Next, we have step 2, compute values of the parametric shape. Okay. And so this is going to be N1, N2, N3, N4. Okay. All right. So N1 here, N1 is 1/4 times 1 minus FG times 1 minus eta G. Okay. Go fast. I'm going to go ahead and copy and paste these. So all that changes is a sign, right? And so N2, we have a plus here. N3, we have a plus plus. And then for N4, we have a plus here. Yes. Okay. Okay. So that's the values of all 4 of our shape functions at our Gauss points, right? Okay. That's good. Any questions so far? I'm just kind of chugging right along here. Okay. All right. So let's do step 3. So step 3, of course, is our shape function derivatives in parametric space. Okay, so this is where we're going to write a lot of code because we have 8 shape function derivatives to take care of. Okay. Okay, so let me do it like this. So we'll do dn1 dx. Go ahead and copy and paste this 4 times. Okay. And we're just going to plug in the formulas just for this. Okay. So we have minus 1/4 times 1 minus eta G. Okay. Go ahead and copy and paste this. These 2 are positive. And positive. Positive. Okay. And we're going to do the same thing with eta. And so this is going to be dn1 d eta, dn2 d eta, dn3 d eta, dn4 d eta. Okay. You go ahead and fix the signs here. So we have a minus 1/4 times 1 minus, here we have epsilon g. Okay. We have 1 plus eps g. And then 1 plus FG. Okay. And we have 1 minus FG. Okay. All right. So once again, you know, double check the values of these, you know, of these shape function derivatives, right? And so I put them in functional form, right? But these should be the 8 shape function derivatives that we need. And so we have dn1 dx, right, is minus 1/4 times 1 minus eta g. dn2 is 1/4 times 1 minus eta g, and so on and so forth. Okay, so I just kind of implemented that. All right, and just like we did it in the in-class example, I'm going to go ahead and put this in matrix form, right? And so let me say this is dn1 dx. Okay, so that's the first row in the matrix. And so that's all of our shape function derivatives with respect to epsilon. And then we have all of our shape function derivatives with respect to eta. Okay. All right, so that's step 4. And so step 4, that's how we implement that in MATLAB. Or step 3, excuse me, that's step 3. Okay. Now we do step 4. Step 4, we're going to compute the physical coordinates of the Gauss point. And so this means we're going to compute xg and yg. Okay, so xg here, we're going to compute. We already have x1, x2, x3, x4, right? And we have n1, n2, n3, and 4. And so let's just go ahead and multiply them. So x1 times n1 plus x2 times n2 plus x3 times n3 plus x4 times n4. Okay. And same thing for y. So let me just go copy paste. It's time. Oops. Okay. So now we have xg and yg. All right, so that's all the hard parts. And so all the hard parts are done. Now we're just going to let MATLAB kind of take over for us. Okay. Step 5, compute Jacobian and all Jacobian related paraphernalia. Okay, so let's start Jacobian first. And so I usually like the symbol Jack for Jacobian just because, you know, J is a little bit too short. Okay. And so Jack here, the way that we're going to compute it is we're going to take our shape function derivative matrix. And so we take dn mat, okay? And we're going to multiply it by our coordinate matrix. Where did I put it? I put it right here. Okay. Okay. All right, so that's our Jacobian, just one line of code, right? And so it looks like a daunting computation, but we just did it in one line. Okay, so next thing we're gonna do is we need to compute the determinant. And so we take determinant of J, we call the determinant function in MATLAB. Okay. Next thing we're gonna do is we're gonna compute the Jacobian inverse. Okay. Let me call this Jack inverse. And so similarly, we're just gonna use the inverse function and we're gonna take the inverse of our Jacobian. All right, step 6. Step 6 is compute shape function derivatives in physical space. And again, this is a simple multiplication. And so what we can say is d and d phys. Okay. This is going to be our Jacobian inverse, just like we have in the in-class example. And so we have Jack inverse multiplied by our dn mit. And those things are computed for us already. MATLAB will give you this this weird thing right here because it doesn't like, even though it's a function that exists within MATLAB, it doesn't like you using it, you know. And you know, if you're interested in learning why, you know, we can talk about it, but don't worry about it. It's just a warning. So I know MATLAB will probably underline it in red, but don't worry about it. All right, step 7. So step 7 is to compute the thermal generation. Okay. We'll call this SG. Okay. And for this particular problem, our thermal generation function is 20 times xg plus 10 times yg. Okay. Right. Again, just, you know, one line of code. We've already kind of done all the hard work up here. Okay. All right, and so the last step here is just to save it out. Okay, and so I should probably establish something here. Okay, so we can say that KE zeros 4. Okay. FE zeros. I'm just putting placeholders for these now. Okay, and so FE is going to be a zeros matrix as well, 4, 1. Okay. Okay, so let's go ahead and save these out. And so we can say is KE is equal to KE plus, and then we're going to add our contributions together. So first thing we have is step 6. We have dn, dphys. Okay. And of course, we're taking the transpose of this. And so the MATLAB operation for transpose is this: you put an apostrophe. Okay. Okay. Then we're going to multiply by k, then multiply by the shape function derivatives matrix again. Okay, but the untransposed version. Okay. Then we're going to multiply it by the determinant of J. Okay. Right. Then you're going to multiply by the weight, right? And so we have the Gauss weight here. But since we're using a 4-point Gauss rule, our weight's just going to be 1. And so I'm just going to leave it off. Okay. So let me leave a note. Gauss weight is 1. And we're going to do the same thing for FE. So for FE, oh, I don't have a matrix for this. Let me go put this in the matrix. And so all I did there was I just put all of our shape functions into a matrix. And so this is going to be that transpose multiplied by SG multiplied by determinant of Jacobian. Again, multiplied by the weight, but our weight here is just 1. Okay. All right, and so that should be parts 1 and 2 of the project. I mean, minus all the bookkeeping stuff, and so you guys still have to do the Dirichlet boundary conditions and things like that, but that should get you past the algorithm. Okay, and so I'm gonna go ahead and post this, and so hopefully it works. It should work, but this was very I was kind of deciding kind of midway through the example to kind of do this, and so hopefully this is helpful to you guys, because I know it's one thing to understand the theory, but to take that theory and implement it in MATLAB is also kind of another step, another ordeal. Okay, I would say that's definitely an important part of this class to know that, but I do want to give you something to get you started. Okay, that said, this what I've implemented here, this is for a quadrilateral, right? It's going to be different for your project, and so the project is a triangle. It's not a quadrilateral, and so details of this algorithm are going to change, right? So first of all, you only have 3 nodes in a triangle, and your shape function is going to be different. Okay, but the same logic should still apply. So you're still going to follow the same algorithm, and do everything. Okay. All right. Any questions on this? Okay, so we have 15 minutes left. So let me go ahead and talk about triangles a bit. I'll save the Neumann boundary conditions for next week. And so, I know I said we'd be done with all the content today, but I also didn't plan to write a MATLAB script right in front of your guys' faces. And so let me talk about triangles for a bit, because I think that we can get done in 15 minutes. And then next week, we'll talk about the Neumann boundary condition. Right? And so I think, that hopefully should get you started. If you want to start with parts 1 and parts 2 of the project now, and then part 3 of the project you can work on next week. Okay. Of course, you're welcome to start working on part 3 right away, but we'll actually formally talk about Neumann boundary conditions next week. Okay. And so let's spend a bit of time talking about ISO. Isoparametric. Okay. And so, we've spent, the last few weeks, developing this isoparametric theory, but we've been doing it for a quadrilateral. Okay. But we know, just by using finite elements, that there are lots of different shapes out there. Okay. The other primary 2D shape is the triangle. Okay. And we can, and just because the triangle is a different shape, we can still apply the same isoparametric theory to triangles, okay? Okay. And so here's the idea. And so, you might have a generic triangle here. Okay. Okay. So nodes 1, 2, and 3. But when you compute the element stiffness matrix and element forcing vectors, you want to do so in the parametric space. Okay. And so you're going to map this to a standard triangle. Okay. The standard triangle looks like this. Okay. And so this is node 1, this is node 2, this is node 3. Okay. And the coordinates for this triangle is that we have 1, 0 here. Node 2 is at 0, 1. And node 3 is at 0, 0. Okay. Whereas this epsilon and eta. And in the physical coordinates, we have x1, y1, x2, y2, x3, y3. All right. And so the first question is, what are the shape functions for this isoparametric triangle, right? And so because this triangle looks different, the shape functions are going to look different as well. Okay. You'll be happy to know that the shape functions here are actually a lot simpler. Okay. So M1 of epsilon and eta, okay, this is just going to be epsilon. Okay. And N3 is just 1 minus epsilon minus eta. Okay. Okay. And so I won't write them all here, right? But what you'll notice is that, because these shape functions are just pure linear functions, there's no cross terms to them. When you compute the shape function derivatives in the parametric space, you're going to get constant values. Okay. And so this is mostly relevant for step 3 of the algorithm. Okay. Okay. So keep that in mind when you're doing your project. Okay. All right. And so that's one big difference. The shape function is going to be different. But the other big difference is that, because our domain is a different shape, right? We're not working on a square anymore. Our Gauss quadrature rules are going to be different as well. Okay. So here are the rules. Okay. Right, and so I have a nice convenient table for you in the notes. Okay. All right, so first we start with the standard one-point rule. Okay. All Gauss quadrature algorithms have a one-point rule. Okay. And so the location for the one-point rule is going to be at 1/3 and 1/3. And so epsilon 1 is equal to 1/3. Eta 1 is equal to 1/3. Okay. And the weight that you apply here is just 1. Okay. All right, next we have the 3-point rule. That's the next step up. Okay, so we have epsilon 1, 2, and 3. Okay, so we have eta 1, eta 2, eta 3. And so this is 1/6, 2/3, and then 1/6. Okay. Okay. And all of these will have the same weight. So all of them will have a weight of 1/3. Okay. And so keep that in mind. Okay. And so when you're doing your project, your weights are no longer going to be 1 because the rule that I'm going to ask you guys to do in the project is going to be this one. Okay. Right. But just for more trivia, or in case if you're interested, you can use this this method in your project as well. Okay. And so we have a 4-point rule. Okay. And so we have epsilon 1, epsilon 2, epsilon 3, epsilon 4. This is 1/3, 0.6, 0.2, 0.2. Okay, eta 1, eta 2, eta 3, eta 4. So this is 1/3, 0.2, 0.6, 0.2. Okay. Unfortunately, the weights here are not so nice. Okay, and so weight 1 here is actually negative, which is very interesting. Okay, so minus 0.5625, and W2, 3, and 4 are all the same. So W2 is 0.5208, 0.5208. 1.5208. Okay. All right. And so if you're feeling adventurous, you're definitely welcome to use a 4-point rule, but the minimum of what I'm requiring you for the project is just the 3-point rule. Okay. All right. And so that's it. That's really all to say about the triangles. And so, besides the shape functions being different and besides the Gauss rules being different, you're going to follow the exact same process that we just went through, right? So first on paper and then also in code. Okay. And so when you do your project, you're just going to have to make the adjustments for these triangular shape functions and the triangular Gauss quadrature rules. Okay. All right. Any final questions today before we wrap it up? Okay. All right, so hopefully that was helpful. I totally did not plan to do the coding today. That was just something that just kind of sparked me in the moment. And so hopefully that's useful for you guys. I'm gonna go ahead and post that code right after the class today. You'll be able to find it in week 15. Okay. If you're here in person, I have your exams, so you can come by and pick it up. Okay. And if you're not here today, I'll bring the exams next week too, so you can pick it up then. So, right? So thank you everyone for coming in today. You guys probably should get started on your projects, and so if you have any questions regarding that, please let me know. I'm always happy to help. So have a great weekend, everyone, and I'll see you guys next week. Okay. All right, sounds good. Oh, really? Let me see. Oh, you're right. Yes. So when yes, there should be Jeff. Ah. Yeah. Yeah, it should be in my office. And so if you want to come by, I think some people had some questions today. And so you can come by. If you have to go now, then you can come by another time. Okay. I'll bring them next week too. Mhm. Yeah, Sam. So someone just pointed that out to me. And so when I computed the Jacobian or the determinant of the Jacobian, that's not you guys. I put determinant of J. But it should be determinant of J. Yeah, so what MATLAB is doing, it's looking for a variable called J, but it doesn't exist. And so it should be determinant of Jacobian. Yeah. Yeah. Good night. Sam, Marilyn, any final questions before we wrap it up today? Okay, all right, so I'm gonna go ahead and close the call. All right, yeah, no problem. All right, see you guys.